In this lecture, I am going to talk about something which is familiar to all of you, at least all of you who have crossed high school. Vectors, as you all know, are extremely important in physics and mathematics. But I'm not going to talk about their physical or mathematical uses. In this lecture, I'm going to talk about a bit about their history. So, as you can see, the title of my talk here is Where Did We Get Vectors From? And to begin answering this question, we will start with another question. Now, how do we usually represent a vector? By usually I mean, say, when you're in high school or in the first year in college. Well, typically what you do is you choose a coordinate system with three axes, x, y, and z, perpendicular to each other. Then you draw unit vectors along these three axes, the so-called I hat, j hat, and k hat vectors. And using these vectors, you can break up any vector, say the vector v here, in the form vxi plus vyj plus vzk. All of you are very familiar with this particular way of decomposing a vector into components. And that really is not my concern right now. I would like to ask you a question which may seem very trivial at first, but which actually is rather deep, at least deep in historical significance. Why do we call these unit vectors along the x, y, and z axis I hat, j hat, and k hat? Now you may say that that's a rather stupid question to ask. After all, I, j, k are three consecutive letters of the alphabet. So why not use I, j, k? To that, I would counter why not use x hat, y hat, z hat. That would definitely seem more natural. Or why not even a hat, b hat, c hat if all we are doing is using three consecutive letters? Why I hat, j hat, and k hat in particular? And to answer this, we will actually have to take a look back at the history of where vectors really came from. So how did physics, and indeed mathematics, get its vectors? But to answer this, we have to go back in time, but we will go back in time a lot further and start with a quick history of numbers. Although, let me be very frank here, what I am going to describe to you right now is not really an ancient history of numbers. As you can see, in the title, both ancient and history is written in quotes. What I'm going to talk about is what would have been the history of numbers if a mathematician had been in charge of history. That is, of creating history. Real history is way more complicated than what I am talking about or what I'm going to talk about right now. There are lots of detours, false steps, lots of discoveries, rediscoveries, intrigues, and all that. And that would be a fascinating subject in its own right. But because of shortage of time, and also because we want to keep this discussion focused more on vectors, what I will do is I will pretend that the way in which I'm going to describe things now is the way in which various kinds of numbers were invented. That is the way they should have been if, say, the history had really followed a nice linear pattern. So in the beginning, there were integers. Leopold Kronecker, a famous mathematician, had said, God created the integers, everything else is the work of man. So, God created the integers. Or did she? Because if you really think about it, the integers are really not that God-given. What is more natural are, as the name suggests, the natural numbers or the counting numbers 1, 2, 3, 4 and so on. Now, let's now try to pretend that we have jumped a few millennia and we can write algebraic equations now. The equations like x plus 2 equals 3 can be written entirely using natural numbers. Other than the symbol x, everything else in the equation is a natural number. And you can solve it in a natural number. In the set of natural numbers, as you can obviously figure out, the solution to this particular equation is x equal to 1. But you can also write equations using natural numbers and natural numbers only, which cannot be solved using natural numbers. Equations like x plus 2 equals 2, or even worse, x plus 3 equals 2, cannot be solved in natural numbers. But now that we have learned about natural numbers, if we want to be able to solve equations written in natural numbers, we see that natural numbers alone is not enough. We have to go beyond that. So to solve equations like x plus 2 equals 2, we have to invent the number 0. And to solve the equations like x plus 3 equals 2, we have to actually invent negative numbers. Now this is, of course, a huge oversimplification. The history of the invention of 0 is a fascinating topic in its own right and would require a full lecture, if not a series of full lectures, to be able to do justice to it. But let's pretend, as we said, that this is how things progressed. Man invented 0 and negative integers, and now we get the whole of the set of integers, not just natural numbers, the counting of natural numbers, 0, and the negative integers. All together gives us the integers. Now, we can all again start writing equations using integers. And equations like 2x equals 6, for example, which is written apart from the symbol x, everything else here is an integer. This can be solved in integers, right? X equals 3, which is an integer. But if integers were all you ever knew, equations like 2x equals 5 have no solutions. So how do we handle that? Well, man invented rational numbers just to get solutions of equations like 2x equals 5. And thus, the integers which we started with, or rather natural numbers which were augmented to integers, have now gotten further extended to the set of all rational numbers. But as you all know, you cannot solve all equations that you can write down with rationals in terms of a rational number. For example, x squared equals 2. Every piece of it other than x itself is a rational number. But you cannot solve x squared equals 2 using only rational numbers. Now, once again, the history of irrational numbers, one of the prime examples of which is square root of 2, is in itself fascinating, has a lot of nice and perhaps not so nice stories associated with it. But let's just cut to the fact that we ultimately end up with irrational numbers as well. And when you add the rationals to the irrationals, you end up with this new set of real numbers. X squared plus 1 equals 0. Now, we're continuing along this fashion. And now you have a situation where you have an equation which is written entirely in terms of real numbers, but has no solution in real numbers. To solve this issue, we have to invent the set of all complex numbers, C. And now this chain apparently comes to an end, because there is something called the fundamental theorem of algebra, which says that any polynomial equation that you can write down with complex number coefficients will always have at least one solution in the set of complex numbers. You can extend that to further prove that it actually has exactly n solutions if n is the highest power in the polynomial, but at least a solution exists. So in order to solve equations written down using complex numbers, we do not need to invent new kinds of numbers. So we would perhaps stop here. If this were the entire history of mathematics, we would have only gone up to complex numbers and no further. But as it turns out, we actually did go a lot further. In order to see why, we will first take a slightly deeper look at the complex numbers themselves. As many of you may have felt when you first saw complex numbers, they're rather strange objects, and in fact, they are unreal. In fact, that's exactly why we have real numbers and imaginary numbers. Numbers whose squares are negative numbers. something which is really difficult for us to cope with at first glance. Now, when complex numbers were first invented, lots of mathematicians had their doubts as to whether you should at all ascribe number-like properties to these things. The person who actually made complex numbers really respectable was somebody called Sir William Rowan Hamilton, one of the most famous mathematicians and physicists of his era. Now, he came up with a new algebra which involved not a single number, but a pair of real numbers. Note that by the time everybody were very comfortable with real numbers, they knew all their properties. So pairs of real numbers also are pretty straightforward and easy and fun to play with. Now, what he did was not only did he decide to call the set of all such pairs of real numbers, pairs A, B, the set C, that was the name he gave them, he also figured out ways of adding and multiplying pairs. So this is how you do math with the pairs. You define addition simply by this rule that A, B added to C, D is simply A plus C, B plus D. First components add, second components add on their own. So as far as additions were concerned, pairs of numbers were just that, pairs of numbers. The first term in the pair sort of added on its own, the second terms added on their own. Now, in addition, he defined multiplication by the following rule. A, B multiplied by C, D was defined by Hamilton to be the pair given by AC minus BD and AD plus BC. Now, you must have all realized what is being done here. A, B and C, D are really nothing but shorthands for A plus IB and C plus ID. And you're using I square equals minus 1 when you're carrying out the calculation and essentially separating out the real and imaginary parts. But note that in all of this, Hamilton never mentioned something like square root of minus 1. He just had a way of multiplying and adding pairs. Now, what is very important is once these definitions are accepted, this set C becomes a field. Not only can you add or multiply such numbers, you can actually divide by them. So these pairs allowed division. Just to take a look at what these properties meant, if you look at a particular subset of C, you look at R tilde, we are going to call that subset R tilde for the time being, of all pairs for which the second element is exactly 0. So all elements of the type A, 0, where A is a real number. Now it's very easy to see that this set essentially is a set of real numbers. If you add two such pairs A, 0 with B, 0, the second term, the second part of the couple stays 0. The first part becomes A plus B. It's just two numbers adding with each other. What's more important is that if you look at the multiplication rule, A, 0 times B, 0 would simply be AB, 0 according to this rule, which means even multiplication wise, the pair with the second term 0 essentially behaves like the real number, which is just given by the first term. So this is what we mean when we say that this subset is essentially the same as the set of real numbers, or more technically, we say it's isomorphic to R. The isomorphism, the map which takes you from this set R tilde to R, the set of real numbers, is obvious. You just map A, 0, the element, to the real number A. Now, what's important is that if you now take another kind of number, another pair, 0, 1, and multiply it by 0, 1 according to this rule, it's going to be 0 times 0 minus 1 times 1, 0 times 1 plus 1 times 0, minus 1, 0. So 0, 1, this pair, according to this multiplication rule, multiplied by itself gives you a number which is essentially minus 1, Remember, a comma 0 is essentially the same as a. So, the square root of minus 1 essentially is a standard element of this set, just 0, 1. So, once you start with Hamilton's rules for manipulating pairs, the square root of minus 1 comes for free. You do not have to invent a new kind of number for that. A very special pair, 0, 1, does the job for you. And, well, if this were a talk about complex numbers, I would have gone on perhaps to show how everything that you have learned about complex numbers can follow from this. The real reason why I wanted to bring this in is to emphasize that William Rowan Hamilton showed us that complex numbers can be thought of as pairs of real numbers. So why not go in for more than pairs? In fact, there was a big motivation for doing that, which drove Hamilton himself in that direction. And to understand that motivation, we have to first just remind ourselves of the basic geometry of complex numbers. Now, Argand had shown us that you can represent complex numbers by points on a plane. A number z can be written either in the so-called rectangular form, x plus iy, real part plus I times the imaginary part, where x and y are nothing but the coordinates of this point on the plane. It can also be written in the form r to the I phi, the so-called polar form, where r is nothing but the distance of the point z in the plane from the origin, and phi is the angle which the line joining the origin to this point makes with the z-axis. Now, I'm assuming that all of you are familiar with both these ways of representing complex numbers as we go along. Now, one very important consequence of this result is that if you multiply a complex number, say r e to the I phi, this red point here, by e to the I theta, which has cos theta and sin theta as the real and imaginary parts, what you are going to get is the number r e to the I phi times e to the I theta, that is r e to the power I phi plus theta. And so, what happens is this angle phi becomes phi plus theta. The point gets rotated through an angle theta. So, every point in a plane can be turned around simply by multiplication through an angle, by a phase factor e to the power I theta, and that's going to cause a rotation through an angle theta. Now, the obvious question to ask, in fact, that was the obvious question which motivated Hamilton at that point, is can this be generalized to 3 dimensions? Of course, Hamilton was not worried about 4 or 5 or higher dimensions at that point, but he definitely was worried about 3 dimensions, which is the dimensionality of the world that we live in. Now, there was one major problem with this attempt. As you know, multiplication, ordinary multiplication, is commutative. A times b is the same as b times a. Well, multiplication by complex numbers also is commutative, as you can easily check from the basic definition of multiplication of pairs. A comma b times c comma d and c comma d times a comma b end up giving you exactly the same pair as a result, something which follows directly from the rules that we had written down. However, rotations in 3 dimensions do not commute. Now, this is a picture which should make this clear. Notice that we have started with a book which is placed in a particular manner, and what we are going to do is we are going to carry out 2 successive rotations. We have marked out the axis. This is the x, this is the y, and this is z axis. And if we first rotate this book through 90 degrees about x-axis, it's going to turn around and you're going to get it to this shape. Now let's rotate it about y. That is, first through x by 90 degrees, then through y, about y through an angle of 90 degrees. Remember, this is the y-axis, the vertical one. When you turn this book about this vertical axis through 90 degrees, it ends up looking like this. So first a 90 degree rotation about x, then a 90 degree rotation about y takes you from this position, let's take the book from this position to this final position. Now what if we did it the other way around? First rotated about y through 90 degrees. That's going to turn the book around in the exit plane. It's going to end up looking like this. And then if we rotate about the x-axis, the book is going to turn around and it's going to face you like this. As you can see, the effects of two successive rotations, the same two rotations but carried out in different orders, are entirely different. So rotations in 3D do not commute. So multiplication will give you rotations in 3D. That idea seems to be dead in the water to begin with. After all, who doesn't know that multiplication is commutative? But this did not stop Hamilton, because he also knew that, after all, not everything in the world is commutative. Maybe he should be able to figure out a new kind of number whose multiplication does not commute. AB is not equal to BA for this, maybe for this new kind of number. But what is also important is that since rotating points in a plane which can be described by two coordinates, a two-dimensional plane, can be done by a special kind of complex number, a pair of real numbers. If you wanted to do this in 3 dimensions, you would definitely have to go beyond pairs. And the obvious choice was that you should generalize to new kinds of numbers which would be no longer couples or pairs, but triplets. 3 numbers which go together. And Hamilton actually struggled a lot trying to figure out a way in which he could multiply triplets. Adding triplets is easy. If you have A1, A2, A3 in one triplet and B1, B2, B3 in another, you could simply say A1 plus B1, A2 plus B2, A3 plus B3 will be the way in which you add them. That's straightforward. But if you had 2 such triplets, he wanted to find a multiplication rule which will have to ultimately give you the field structure. That is, not only should the multiplication be defined, you should be able to divide by each complex number at each of these special triplet numbers, as long, of course, as the number wasn't 0. Now, of course, if you want triplets, you need one more imaginary part. Now, since the imaginary part had an I in front of it, I standing for imaginary, the obvious thing would be to call the next second kind of imaginary part a J. Now, the triplet struggle was a very real one. In fact, this is something which Hamilton wrote in a letter to one of his sons. Every morning in early part of October 1843, on my coming down to breakfast, your brother William Edwin and yourself used to ask me, "Well, Papa, can you multiply triples?" Whereto I was always obliged to reply with a sad shake of the head, "No, I can only add and subtract them." And this continued for quite some time. Hamilton could not find a satisfactory way of multiplying triplets. Indeed, we know today that this simply cannot be done properly. Inspiration struck Hamilton while he was out on a walk with his wife on October 16, 1843, apparently as they were crossing the Brougham Bridge on a royal canal that runs through his hometown of Dublin. And the inspiration that struck him was basically that you could not get a field out of triplets, but you could out of quadruplets or quartets. And so instead of one imaginary, as with complex numbers, or the pair of imaginaries ing that he was trying out, he needed 3 imaginaries, I, j, and k. So 3 imaginaries will work, whereas 2 imaginaries will not, and he realized the rule that he needed. Of course, the reason why this inspiration struck him so suddenly was that he had worked for hours and hours, almost day and night, trying to make 2 imaginaries work, and once his 3rd imaginary idea struck him, he could get the thing to work almost immediately. And in one of the best known examples of mathematical vandalism, what he did was he picked up a stone from the roadside and curved the formula for a new number system on the bridge's wall. The original bridge no longer stands. There is a new bridge in its place. And, of course, Hamilton's original scribblings are gone. But a plaque had been put down in the new version of the Brougham Bridge, which says, "Here, as he walked by on the 16th of October 1843, Sir William Rowan Hamilton, in a flash of genius, discovered the fundamental formula for quaternion multiplication. 4 parts, real part, 3 imaginary parts, 4 parts, a number in 4 parts. That's why these numbers were called quaternions. And below that, Hamilton's brilliant insight was written down. These imaginaries I, j, k would have to obey a rule. And the rule would of course be I square and j square and k square. All of the 3 will be -1. They are imaginaries after all. But in addition, he also needed one more rule. The product of I, j, k is -1. Now it turns out that this is enough to figure out everything about how to multiply 2 general quaternions. Note that from this basic defining principle, you can also figure out things like ij. That's pretty easy because note that ij is the same as -ijk square. Now, one important thing, this new rule for multiplication, Hamilton did not assume that it's going to be commutative, but he did assume that it has to be associative. Associativity is a property that we are all familiar with. Even our ordinary daily language also deals with things like this. Remember, things like, okay, now let's go back to ordinary numbers. Things like addition, subtraction, multiplication, and division, familiar operations all, are actually binary operations. You're supposed to take 2 numbers, carry out the operation, get another number, right? But that does not prevent us from saying something like add 3, 4, and 5, or multiply 7, 8, and 9. Notice that you would never say subtract 3, 4, and 5, or divide 7, 8, and 9. Because in the latter cases, the bracketing matters. That is, 3 minus 4 minus 5 is very different from 3 minus 4 minus 5. Or 7 by 8 divided by 9 is not the same as 7 divided by 8 by 9. For addition, on the other hand, 3 plus 4 plus 5, same as 3 plus 4 plus 5. The same goes for multiplication. This is what the associative character tells us. You can put the bracket wherever you want. Whichever pair you want to handle first, you can. It will not matter. And that is exactly what Hamilton demanded of his new kind of numbers as well. So this result that we have, that ij k square is -1, actually is ij times k square is -1. But because you can remove the brackets or place the brackets anywhere you want, also say that this is the same as ijk times k. Now ij times k square is not -1. I made a mistake there. Ij times k square is minus ij. So minus ij is going to be ij times k square, ijk times k, that is minus k, because ijk is -1. So minus ij is minus k, so ij is k. And very similarly, we can figure out that jk will have to be I, ki will have to be j, and lo and behold, if you try calculating ji using this procedure, it will take you a bit more effort, but you should be able to do it yourself. Ji will turn out to be no longer k, but minus k. So as you see, the multiplication does not really commute. ij and ji are different. Kj and jk are also different. There's a change in sign. Ik and ki are also different in sign. Now you might be tempted to say that this means that the multiplication of these 4-component objects or quaternions is anti-commuting, but that also is not true. After all, real numbers, remember, quaternions have a real part. And the real part commutes with I, j and k. So parts of it commute, parts of it do not. So these new numbers of Hamilton were quartets, as we said, called quaternions. So typical quartet would be A0, A1, A2, A3, which is same as A0 plus A1i plus A2j plus A3k. And if you multiply two such quartets, say A0, A1, A2, A3, with B0, B1, B2, B3, all Hamilton had to do was to assume that the multiplication obeys standard properties, the same kind of properties that you would expect from ordinary numbers, except for commutativity, that is. You should be able to break up the bracket. Technically, we say this product is distributive. So A0 gets to multiply the whole thing, A1i gets to multiply the whole thing, A2j gets to multiply the whole thing, and A3k gets to multiply the whole thing. And you sum up all of these together. Now, when you do this multiplication, this gives you A0, B0, plus A0, B1i, plus A0, B2j, plus A0, B3k. On the other hand, here you get A1, B0i, A1, B1, I square, that's minus A1, B1, that goes with the A0, B0. Then A1, B2, ij, that is A1, B2k, A1, B3, ik, that's minus A1, B3, j. Now we can carry out this entire multiplication, gather the terms with 1, that is the real part, I, j and k together, and I would get this whole new way of multiplying to quaternions. To summarize, Hamilton had the following rules, that I square, j square, k square, and ijk were all minus 1. That gave ij equals k, jk equals I, ki equals j, ji equals minus k, kj equals minus I, and ik equals minus j. And using these and assuming distributivity and standard properties, the product of two quaternions worked out to be a number where you could figure out the real part and the three imaginary parts separately, rather straightforwardly, just by using these rules. Now, before I go any further, let me point out how you could deduce from this rule that division by quaternions were possible. Of course, when you say division is possible, all you really need to show is that given a quaternion q, you should be able to find a quaternion which is 1 over q, or q inverse, something which when multiplied by q gives you 1. In this case, 1 is simply 1 plus 0 into I plus 0 into j plus 0 into k. Let me remind you how this could be done with complex numbers. In fact, I just asserted that complex numbers became a field under Hamilton's way of multiplying them, but I did not really prove that you could find a reciprocal of every complex number which was not 0. Well, I'm pretty sure all of you know the proof, but recapitulating that might give you a good way of figuring out what to do for quaternions as well. Given a complex number z, x plus iy, you just form what is called its complex conjugate, something with the same real part but negative imaginary part, x minus iy. Now, if you multiply x plus iy by x minus iy, just by treating I square as minus 1 and using the standard rules for multiplication, or taking these two complex numbers as pairs x comma y and x comma minus y and using Hamilton's rules for multiplication of pairs, either way, you're going to get the result that this is going to be nothing but x square plus y square, the real number. So, z times its conjugate gives you x square plus y square, which is not 0 unless x and y are both 0. That is, unless the complex number itself is 0. Now, this immediately shows us that the conjugate of z divided by x square plus y square, the so-called magnitude square of the complex number, is actually the inverse of z. If you multiply z by that, you're going to get the number 1. Of course, once you've got the inverse, it's easy to divide. Now, for complex number inverses, this is the way things work, and something very similar happens for quaternion inverses. Given a quaternion Q with the quartets being the quartet of numbers being A0, A1, A2, A3, that is the number being the quaternion being A0 plus A1i plus A2j plus A3k, we will define Q bar, its conjugate, quaternion conjugate, as A0 minus A1i minus A2j minus A3k. Same real part, all the imaginary parts change sign. Now, if we were to multiply these two things together using this set of rules, it's pretty straightforward to work out. You will find that the result is something which is again very similar as what you get with complex numbers. Q bar Q, this product, simply works out to be A0 square plus A1 square plus A2 square plus A3 square. You call this a length of the quaternion Q squared. Mod Q is a symbol for length of the quaternion Q. And ultimately, what this tells you is that if you multiply a quaternion by its conjugate, you are going to get a real number, which is not 0 unless A0, A1, A2, A3, that is Q itself, is 0. So for any non-zero quaternion Q, if you just form the Q bar and divide it by mod Q square, which is a non-zero real number, you have got its inverse. And that means you can divide by any non-zero quaternion. The field part checks out. Now, a special kind of quaternion would be one in which there is no real part. That is a purely imaginary quaternion, so to speak. Actually, people call these pure quaternions. No real part, just something into I plus something into j plus something into k. That is, if Q1 and Q2 were pure quaternions, their real parts A0 and B0 would be 0. Now, if you look at this rule for multiplication of two quaternions to general quaternions and use the fact that A0 and B0 are both 0, something rather strange happens, or something rather familiar should emerge. That is, if you took... Okay, but before that, if you were to add two such quaternions, obviously they would just add component by component. A1i plus A2j plus A3k added to B1i plus B2j plus B3k would simply be A1 plus B1i plus A2 plus B2j plus A3 plus B3k. No surprises there. The product would be simply something like this. This term would drop off. You will get minus A1 B1 minus A2 B2 minus A3 B3. What about the I part? These two terms would drop off because A0 and B0 are 0. So you would get A2 B3 minus A3 B2. Here, this term and this term would go away. You'll get minus A1 B3 plus A3 B1. And here you will be left with A1 B2 minus A2 B1, multiplying I, J and K. Now, for those of you who are familiar with vectors, at least the products of vectors, this should come as quite a surprise, because if you look at the real part of this product, apart from a minus sign, that's exactly what you call the dot product of two vectors with components A1, A2, A3 and B1, B2, B3. And of course, it doesn't even end there. These three terms that you get are exactly the components of the cross product. So if you start with two pure quaternions, multiplying them gives you both the dot product and cross product of vectors at the same go. Now remember, one of the first things you have been taught perhaps when you're dealing with vectors is that scalars, that is numbers and vectors, are two different kinds of objects, and you should never add them together. Here, on the other hand, if you deal with quaternions, scalars, at least the real part, and the so-called cross product, which is a vector product, seem to be added together with perfect ease. And indeed, that's the way things used to be when Hamilton had worked with quaternions. In fact, at this time, Hamilton was at the peak of his fame. He had already done lots of work in mechanics, Many of you may have heard of Hamiltonians, even if you haven't dealt with them. At least in quantum mechanics, Hamiltonians play a huge role. Actually, they played an even huger role in classical mechanics. He was also very well known in the mathematics circles because of his work with graphs and all that. So, coming from this very famous person, his ideas caught on really, really fast. Now, a similar system was discovered by a German school teacher, Hermann Gunther Grassmann. A very similar idea, but actually which turns out to be much more powerful than just quaternions. However, nobody paid much attention to Grassmann's ideas at that time, simply because he was a lowly school teacher compared to somebody who is actually a star of the scientific community at the time. Also, he published his work in a rather obscure journal, which almost nobody read. Grassmann's work made a huge comeback later on, but that's really not part of our story. What's more important to us is that among many people who used quaternions, Hamilton's quaternions, there were a lot of people who actually used pure quaternions a lot. The quaternions for which the real parts were zero. Peter Guthrie Tate and James Clerk Maxwell led the charge here. You may or may not know much about Tate today, but Maxwell, of course, should be a household name. And in fact, all of his laws of electromagnetism, his work on wave equations, electromagnetic waves and all, was done originally using pure quaternions. Now, two followers of Maxwell, Hamilton, etc., Josiah Willard Gibbs and Oliver Heaviside, independently came up with this idea of dropping the scalar or the real part of quaternions completely, giving rise to modern vectors. So you have just A1i plus A2j plus A3k, no A0 at all. And Gibbs and Heaviside essentially said that we will work only with pure quaternions. That of course meant scalars and vectors could no longer be added together, but product of two pure quaternions being the sum of a scalar and a vector part, or a pure quaternion part, became two separate things. In their version, you ended up with the scalar product and the vector product, the dot and the cross. Now, quaternions have since then gone into a decline. They are not used that often nowadays. Although, remember, as I said, they are used primarily to rotate things in 3 dimensions. And one place where you need to rotate things in 3 dimensions rather fast is when you're writing computer games. So in the computer games industry, when you code for realistic looking video games, you actually need to use fast algorithms for rotating things. Their quaternions play a very important role even today. But in mathematics and physics, their importance have gone down a bit, but their legacy still lives on. By now you must have figured out the answer to the question that we asked near the beginning of this lecture. The legacy of Hamilton's quaternions live on in the notation I hat, j hat, k hat. Remember, I stood for imaginary when we talked about complex numbers. And since you had 2 more imaginaries, calling them j and k was natural. And today, we live with the unit vector names I hat, j hat, k hat as reminders of the quaternion origins for vectors. Now, the history lesson is over, but I do have one final task, a final thing to discuss. We started out by saying that Hamilton actually invented quaternions in an attempt to talk about rotations in 3 dimensions. After all, complex numbers allowed you to rotate in a plane. Hamilton wanted to be able to rotate things in 3 dimensions, and that's why he ultimately came up with quaternions. But what do quaternions really have to do with rotations? Let's explore that next. Now, for this part of the discussion, I will make a small change in the notation. Now that we have learned that pure quaternions without a real part, are essentially the same as what we call vectors, we are going to put arrows just as we put on top of vectors for pure quaternions. Also, we will assume that all of you are familiar with the dot and the cross product of vectors, and as we have already figured out, when you multiply two quaternions, pure quaternions, that's why you have arrows on top of A and B here, you get negative of the dot product plus a vector part or a pure quaternion part, which is the cross product. So what this means here is that we are actually talking about quaternion multiplication. So when we don't use any sign between two symbols and just put them next to each other, the way we write products, we mean product of quaternions. And later on, when we talk of other objects which are not pure quaternions, but quaternions which have a non-zero real part as well, we will just omit the arrow. Of course, we will also use sometimes a hat in place of the arrow when we mean unit vector. Now, notice that whenever we take a dot product of two vectors which are in the same direction, the magnitudes multiply, as we know, and their cross product vanishes. So if A and B were in the same direction, then their quaternion product would simply be minus A times B. A special case of that would be for a unit vector n hat, we get n hat square, n hat times n hat, as simply minus 1. So A, the vector, any vector, can be written down as minus A vector times n hat square. And using the associativity of the product, we can move the bracket from the two ends onto the product of A and n, and we can write this as the same as minus A vector times n hat. Remember, here times is quaternion product. The whole thing multiplied, again quaternion product, by n hat. But an, as we have already seen, is A dot n hat minus A cross n hat with an overall minus sign. The overall minus sign cancels with the minus sign we have here. So this whole product is A dot n hat minus A cross n hat times n hat. Now this result is actually quite familiar to all of us. Note that A vector here is a pure quaternion or a vector as we know it. On this side, this is a number times a vector. There is also something else. This is, of course, still a quaternion product. This thing is a pure vector, but this, you are multiplying that by another pure vector and you are going to get a composition out of it, something like this. But let's just focus on this term. If you are familiar with the geometry of the scalar product, you would know that A vector dot n hat is nothing but the projection of the vector A in the direction of the unit vector n hat. And when you multiply that by n hat, you just get the component of A parallel to n hat. So this other part, the rest of it, must be the component of A perpendicular to n hat. So you can write this as A parallel plus A perpendicular. Note, we have drawn this vector A here, and let's say this n hat, and we have drawn a plane perpendicular, normal to n hat here. This is a plane in green. The component of the vector A in this plane and the component parallel to n hat, these two together add up to A. The component parallel to n hat is this A parallel here, and the rest is the A perpendicular. So A parallel is, of course, this term. The rest has to be A perpendicular. Now, what would happen if we were to reflect this vector A in this plane? Now, that's easy to figure out. If you do not know what happens when you reflect a vector in a plane, just imagine that the wall besides you is a mirror, and just imagine walking parallel to the wall. Your image will move parallel to yourself in the same direction. Whereas if you were to move away from the wall, perpendicular to it, the image will walk away from you in the other direction. So when you reflect a vector in a plane, the in-plane component, which is A perpendicular, the component perpendicular to the normal of to the plane, will actually stay the same. A parallel, which is actually out of plane, parallel to the normal, would reverse. So the reflected vector A prime is going to be given by the same A perpendicular, but a reversed A parallel, minus A parallel, and that's going to give me my A prime, the reflected vector. So A prime is of course minus A parallel plus A perpendicular. So all you have to do is take this expression, reverse the sign of this part. That's what you get. Now, let's say we want to move the n hat to the beginning here in both the terms. Now here you have to be a bit careful. N hat will just move to the front here without any change of sign, simply because A vector dot n hat is just a number, and numbers commute. On the other hand, what about this thing, A cross n hat with n hat? Note that AB and BA are not the same, because AB is minus A dot B plus A cross B. BA is minus B dot A plus B cross A. And this part stays the same. A dot B and B dot A are the same, but A cross B and B cross A are negatives of each other. However, notice what happens here. A cross n hat and n hat. Geometrically, these are two vectors which are perpendicular to each other, which means their dot product vanishes. So if you were to switch n hat to the other side, only the cross product term will contribute, and now when you switch it to the other side, you're going to get a change of sign. So moving n hat to the other side will give you minus n hat A dot n, no change in this term because of the flip, but plus n hat A cross n, this sign has changed to a plus. But now if you take n hat common out to the left, what you are going to get is A prime is the same as n hat times minus A dot n plus A cross n, and this is nothing but the geometric product of the vector A with the vector n. So A prime is nothing but NaN. So what we have found is that if you want to reflect a vector A in a plane normal to a unit vector n hat, all you need to do is multiply n hat by A and then by n hat, using of course a quaternion rule for multiplication. So A prime equals NaN. This becomes our rule for reflection in a plane normal to n. Now, what is that to do with rotations? For that we need to think about one more part of geometry, which is what happens when you do two successive reflections. Of course, the answer is given at the top. Two reflections make a rotation. But let's try to prove that. Let's consider two successive reflections in planes normal to two vectors p hat, unit vectors p hat and q hat, where the angle between these two normals, these p hat and q hat, is theta by 2, this angle. And of course, that means that the planes normal to them, which I have just shown as sections, just lines, because I'm thinking of a slice which contains p and q. So this purple line and the orange line are the two planes which are normal to p hat and q hat. And let's ask ourselves what happens if we were to reflect this particular point, which makes an angle alpha with at least line joining this point with the place where the two planes intersect, makes an angle alpha with our first plane. What would happen if we were to do two successive reflections? The first reflection, of course, will make this point move from here to here, whereas this angle is alpha. When you reflect, this angle on the other side will be alpha. Now, let us think about what happens when you reflect this point in this plane. Of course, for that we need to know what this angle is. But remember, if theta by 2 is the angle between these two normals, then theta by 2 is also the angle between these two planes. So this angle is simply theta by 2 minus alpha. And what happens when you reflect this it goes to the other side through the same angle, theta by 2 minus alpha. So after two successive reflections, the point here, the red point, will ultimately end up at this black point here. What is the angle between this line joining the red point to the place where the two planes intersect with the line joining the black point with the same point? Well, that's easy. Alpha plus theta by 2 minus alpha plus theta by 2 minus alpha. And that, rather surprisingly, is simply theta. What's surprising about this result is that it does not depend on where this point is with respect to this plane. No matter what the angle alpha is, this angle is always theta, and that tells you that every point gets turned through an angle theta. This is a rotation through theta about the line where the two planes intersect. Of course, that looks like a point here because we are just looking at a two-dimensional section, but you can easily imagine extending this to the third dimension. So the line through which the two planes intersect is also the line which contains this unit vector n hat, which is p hat cross q hat. Or the unit vector in the direction of p hat cross q hat to be exact, so p hat cross q hat divided by the magnitude of it. So two successive reflections in two planes with normals p hat and q hat is a rotation through an angle which is twice the angle between the two unit vectors, and whose axis of the rotation is given simply by p cross q, or a unit vector in the direction of p cross q. Now, what happens to this when we use quaternions? The first reflection takes r to r prime, where r prime is simply p hat r p hat. Remember, that's what reflection in a plane normal to a vector does. If the vector is n hat, the reflected vector becomes n hat r n hat. Well, the second reflection would be through a plane normal to q. So r double prime, the result of the second reflection, would be q r prime q. But r prime is prp, so it's q, prp within bracket, then q. So qp r pq, which we can write as capital R capital R inverse, where capital R is simply minus qp. The minus sign is simply there to make contact with what we use otherwise. Because note that, of course, if R has a minus sign, R inverse would also have a minus sign. So the minus sign here doesn't really change anything, it just cancels. Note also that when I say R is minus qp, I mean the quaternion product here. That means this is not a pure vector. It has a scalar part and a vector part. And of course, what we have used here is associativity. So this is qp r pq. The only thing left to show is that R inverse, capital R inverse, is the same as pq or minus pq. Well, that's easy to see that if you were to multiply capital R minus qp with minus pq, the two minuses will of course give you a plus, but what you get is qp times pq, that's q times p squared times q, and p squared is minus 1, so minus q squared, and q squared is minus 1, so plus 1. So if R is minus qp, R inverse is minus pq, whatever you have sitting here. So minus qp simply, as we said, this is not a pure quaternion, neither a number, it's just q dot p minus q cross p. So a scalar part and a pure quaternion or a vector part. If the angle between p and q, as we have said, is theta by 2, then q dot p is simply cosine theta by 2, and minus q cross p is simply a vector which is in the direction of p cross q, same direction as n. Its magnitude is simply sine theta by 2, sine of the angle between the two unit vectors. R, the rotation object. This is what is called a rotor, a quaternion, which allows you to multiply and produce a rotation, but not directly. It's not just the rotor times a vector. It's rotor, vector, rotor inverse. And this rotor is given simply by cosine of half of the angle of rotation plus sine of half of the angle of rotation times the axis, unit vector along the axis. This is the rotor that Hamilton was looking for. This is how you multiply and produce rotations. And just a curiosity, which is actually quite useful when you want to do calculations with it. If you break up cosine theta by 2 and sine theta by 2 in their series, you get 1 minus theta 2 by whole square by 2 factorial plus theta 2 by theta by 2 to the power 4 by 4 factorial and so on from cos theta by 2. A similar series with sine theta by 2. But now, notice that n square being minus 1, you can just pull this in and call this plus theta by 2 whole square by 2 factorial n square. Here into the 4, of course, is plus 1. So you can just plug that in without a change in sign. You would have a minus sign in the next term. Minus theta by 2 to the 6 by 6 factorial. You can pull in into the 6. Remember, n square being minus 1 means into the 4 is plus 1, into the 6 is minus 1. So that will become plus again. Here on the other hand, theta by 2 n hat, that's fine. Here, this minus can be gotten rid of by using the fact that n square is minus 1. So it's the same thing as n hat cube. This will be n hat to the 5 without a change in sign and so on. Now, if you combine all of these terms together, you see that we are actually getting theta by 2 times n hat as powers divided by that power factorial summed up all together, which is nothing but e to the power theta by 2 times n hat. So we can write down a very compact formula for a rotor. All you have to do is take the angle of rotation, multiply that by the axis unit vector, divide by 2 and then exponentiate that. Of course, when you exponentiate, you have to make use of the standard rules of multiplication for calculating powers in the exponential. The rules that you use would have to be rules for quaternion multiplication. Now, just as an example of how this could be quite useful, let me show you how you could combine two successive rotations and find the angle, say, of the overall rotation. Now, this is a pretty straightforward thing to do if the rotations were in a plane. If you do two successive rotations through angles theta 1 and theta 2, the resulting rotation is theta 1 plus theta 2. But that's only when the axis of the two rotations are the same. That is, you're rotating in one plane and one plane only. Things are way more complicated when you rotate about multiple axes. So we are going to try to answer this using quaternions. But first, let's answer the question, what is the combined effect of two rotations? What rotor will tell you what happens when you first apply R1, the rotor, then R2, the rotor. So let the axes and angles of the rotations be n1 hat theta 1 and n2 hat theta 2 respectively. So these are described by the rotors R1, which is e to the power theta 1 by 2 n1 hat, and R2 e to the power theta 2 by 2 n2 hat respectively, which you can write down in this form as we have already seen. Now, what is the effect of applying the rotors R1 and R2 in succession? Remember, when you apply rotor R1, what you are really doing is R1, R vector, R1 inverse. So R goes to R1, R vector, R1 inverse. This is the new vector which you get when you apply the first rotation. Now, when you apply the second rotation on this, it's going to be R2 on the left, R2 inverse on the right. But it will act, of course, on this rotated vector. And now it's easy to see that this whole thing is R2, R1 times R vector times R1 inverse, R2 inverse, but that's the same thing as R2, R1 inverted. The net rotation can be described by a single rotor. R equals R2, R1. Remember, R2 and R1 are quaternions, and when you multiply them, the product is not a commutative thing. So the fact that rotations don't commute is actually borne out by the fact that the commutation rules for quaternions is not straightforward. They don't either commute or anti-commute. They do a mixed kind of thing. Now, just to show what kind of result a calculation would give you, if R is R2, R1, that is, you are multiplying this by this. Now you can just open out the bracket and get a real part cos theta 2 by 2 times cos theta 1 by 2 plus this times this. Of course, the numbers just multiply, you just get n1 hat, and this by this you just get n2 hat, and so on. These are the three terms. And you then get one more term which you get when you multiply these two terms. You get n2 hat, n1 hat. That, remember, is the quaternion product. So minus n2 dot n1 plus n2 cross n1. So now notice that this term is a purely real number. And this is a purely real number multiplied by this real number. So this and this together gives you a real part of the product. Whereas this is a vector, this is a vector. That is a pure quaternion part. And this is a vector. So, when you collect the terms together, this is what you get. This upper line here is a purely real part. The lower line here is a vector. So, the effect of multiplying two rotations through angles theta 1 and theta 2 respectively about axis n1 and n2 respectively is given by this single rotor. And you want to ask, what is the angle of rotation for this combined rotation? The answer is simple. The real part is nothing but cosine theta by 2. So the angle for the net rotation is given by this expression. Cos theta by 2 is cos theta 1 by 2 times cos theta 2 by 2 minus sin theta 1 by 2 sin theta 2 by 2 times the dot product of n1 and n2. Note that if n1 and n2 were to coincide, then n1 dot n2 would simply be 1. And this would really tell you that cos theta by 2 is cos of theta 1 plus theta 2 by 2. That is, it will give us back theta is theta 1 plus theta 2 for rotations about the same axis. What about the axis? Well, you just take this vector part, and if you want the unit vector, of course, you would have to divide by the length of this. I've not bothered to do that here, but you can easily figure that out yourselves. But you can see the utility of this. Pure multiplication would simply give you something as complicated as a rotation. So this, if you have studied rotations in 3D, you would know that it's a pretty complicated thing to do. You would write down a 3 by 3 orthogonal matrix, multiply column vector by that, and so on. It just becomes multiplication of quaternions here. Which is why, as I said, quaternions still live on very practically in places where you need to do a lot of rotations very, very fast, as in the computer games industry. But I hope you have enjoyed this foray into vectors, this foray into their history, as well as into this perhaps unknown thing to you, the quaternions, which still have immense practical application. As I said, Grassmann had a similar idea at about the same time as Hamilton, and that actually was generalized later to a much more powerful structure called geometric algebra. If you are interested, there are plenty of references on the net, some nice YouTube videos as well on geometric algebra, and you can try taking a look at that and learn about a very powerful way in which scalars, vectors, etc., all of them can be added together, can be multiplied together, and in general be manipulated together to give many results much more quickly. But that would be an entirely different story. So let me call it quits today here. Bye for now.